Hi there. My name is Sonali, if you remember. Yes, I really apologize for not being active for the and because my last video that I have uploaded was like more than like a half year ago. So, however, uh, I'm back and actually, I think yeah, I'm going to give a promise that I'm going to uh, upload the videos is much more frequent because now I'm just like doing my PhD, first year PhD in machine learning. And actually, this is very important to, I would say, like to motivate myself to learn more is just like to also at the same time to share all the knowledge that I have with you. And so that I think that will be very cool. Practice to actually like to study at the same time like doing a live so what is the actually today we're going to talk about. The topic is the model evaluation process. The model evaluation process is very important because when we start like doing any training any model, right? Like any machine learning model, whether it be like a binary classifier or multi-model, multi-class classifier, it's or it can be like just, for example, we take one classifier, let's say logistic regression, right? And what's the actual point of the model evaluation? The model evaluation process is uh, has the main goal is just to help uh, to choose the best predictive model for on the which will be used like on the test set, for example, right? So for example, we have trained uh, 10 different models on the training data, right? And we actually we're thinking about what kind of model. This is called a model selection, what we're going what which model we're going to choose, right? Yeah, so in this case, when we say that, this is very important to actually know the fact that this is that will be very very expensive to actually to test each model that we have trained, right, on the test set. So this is actually important to select the best model, for example, like from the which was trained on the on the train data, and then you will pick that one, the best model, the best performing model, and uh, test it like on the test data, right? So this is actually very important to remember, and this is actually going to be very helpful for you to understand all this kind of stuff because we're going to really dive into it. We're really going to dive deeper into that one, how it works, etc. Right? So this is the first thing that I want to talk about. I think it's time to start. Uh, oh gosh. Yeah, I think it's time to start to train the model itself, but not train the model. So let me share the screen. Okay, entire screen. So it must be sharing now. So we go in here to this one, right? Oops, where is it? Here we go. So Okay, we're ready. Let's get started. So, once predictive, so we start to talk about this one, right? Estimating the performance of constructed predictive model, also known as the model evaluation, is essential importance in machine learning. This is because eventually the degree to which the model has utility rests with the estimated predictive performance. Not only are model evaluation methods critical to judge the utility of trained model, but they can also uh, play an important role to reach the model in the first place. The first process of picking the final model among the large class candidate models is known as the model selection process, which I have talked before. And there are some popular model selection techniques that operate based on model evaluation methods. In this chapter, we first cover common model evaluation methods, and then we examine the utility of some of these methods for model selection. Okay, once a predictive model or classifier or regressor is constructed, it's particularly important to evaluate its performance. After all, the worth of a model in practice depends on its performance over all possible future data that can be collected from the same problem for which the model is trained. However, such unseen data can naturally not be used for this purpose, and the only means of estimating the performance of a trained model is to use the limited data at hand. The model evaluation stage, also referred as the model assessment errors, include the methods and metrics to estimate predictive performance of a model. To understand the model evaluation process, it will be helpful to distinguish between the evaluation rules and metrics. Okay. All right. So first, let me check the tenant. Right. So all right, so let's go forward. As a metric is used to quantify the performance of constructed model, for example, in section we saw the error rate of the classifier, which means the probability of classifying an observation is drawn from the feature label distribution governing the problem. However, there are other metrics that can be used to measure various predictive aspects of a trained model. For example, we will talk today about precision, recall, F1 score, and the area under the curve, operating characteristic curve, ROC, or ROC, and the area under the curve. A model evaluation rule, on the other hand, refers to the procedure that is used to estimate a metric. In other words, a metric could be estimated using the various rules. For example, we have previously seen holdout estimation rule to estimate the error rate of the classifier. However, one can use other estimation rules such as resubstitution, cross-validation, and bootstrap estimate error rate. For simplicity of discussion in what follows, estimation rules are described in the section with classification error rate. However, all procedures except when stated otherwise are applicable to estimating classifier and regressor performance metrics. All right. So let's start. Now we talk about model evaluation rules. Here we go. Let S be like your set, the training set, right? So we have x1, which is like your observation, and this is actually the expected value referred to the y1. or static standards they use it. So to highlight the sample size, we will discuss the following estimation rules. So what kind of estimation rules we're going to discuss about is the holdout estimator, resubstitution, bootstrap, simple cross-validation, standard cross k-fold cross-validation, leaving out, stratified, and the shuffle and split random permutation cross-validation. Holdout estimator. To estimate the performance of a learning algorithm on unseen data, we can simulate the effect of having unseen data using the variable training data. As to do so, we can randomly split into reduced training set and test denoted as T. Yeah, it's common to also always set the test set like the test size of 25%. We then apply the learning algorithm to train classifier and test its performance. 2 points to notice: the outcome of applying sub index is used to better distinguish the sample size that is used to training. Because it's not is used anyhow in training, it can be treated as unseen data. This is, however, a special unseen data because the actual label for each observation that belongs known, therefore it can be used to estimate the performance. This can be done by using to classify each observation and to compare the assigned labels with the actual labels and estimate the error rate as a proportion of samples within S and the are misclassified. The model evaluation rule is known as a holdout estimator. The holdout estimate denoted is naturally representative of the performance in the context of which the data is collected. However, we know that is the outcome of applying learning algorithm. Viewing a whole assessment, the performance of learning algorithm outcome would help prevent confusion and misinterpretation, especially in the cases when the learning process contains steps such as scaling and feature selection. As a result, we occasionally refer the estimate of the performance of a trained model as a performance of which is learning algorithm that led to the model. Despite the intuitive meaning of holdout estimator, its use in a small sample, one sample size with respect to feature size small, could be harmful for both training stage and the evaluation process. You see, despite the intuitive meaning of hollow estimator, it's used in samples in a small sample size with respect to feature size. This is because compared with a large sample, in small sample, each observation has generally a larger influence on the learning algorithm. In other words, removing an observation from a small training data generally harms performance of the learning algorithm more than removing an observation from a large training set. Therefore, when n is relatively small, holdout portion could be severely hamper the performance of the learning algorithm. At the same time, we have already a small sample to work with. The holdout estimate is obtained even on a smaller set. Therefore, we can easily end up with the inaccurate and unreliable estimate of the performance, not only due to the end up with the inaccurate and unreliable estimate of the performance, but also because the estimate could be very biased towards specific aspect picked for testing. As well, we'll see later in this section, there are more elegant rules that can alleviate both aforementioned problems associated with the use of holdout estimator in small sample settings. Nonetheless, when to remove harmful impact of holding out portion for testing small samples, uh, once is obtained. Okay, let me first go. Guys, I also have here a DeepSeek chat in which I have asked before a chat to help me to give me examples, provide me examples. So, all right, so I go to like in this one. Let me first like enter. Okay, let's guys let's ask a DeepSeek to yeah, first guys, by the way, yeah, we talked about this one's very cool. However, we'll also have to go to model. Mm, advanced proprietary recognition. We go to a model selection part, feature selection. This one, right? Error estimator, holdout estimator. Okay, you see how it works? Small sample region, right? So this is actually so. How well does design classifier predict? Predictive capacity of the classifier is the only indicator whether scientific knowledge is possible by the design classifier. How does the one estimate classification error, generalization error of a given design classifier? We don't know the true distribution of the data. Error estimation could be involved classifier design and the feature section. So random variable. So yeah, we're noting that this is our classifier and this is actually our data. General observer data which generalized general random pairs. Yes, denoted as attempt this for binary classification. An attempt to design classifiers, design levelization. This to say to construct the classifier. Okay, we have two output classes. Note that it's still a random variable as a function. Classification error. The cognition probability of orphan classification is the classification error is the performance of a design classifier using the data in hand on future observations, right? Yeah. Generally, this is what interesting. But however, the conditional classification is more important because it's kind of expected error is the average performance of a classification rule on future observations or the whole sample space of your experiment. The conditioning error gives us an idea how well, on average, a classification rule performs on a specific problem. Unconditional error can become important in practice if, which happens in variance, if the variance is very small. An error estimator is mapping, where it specifies internal random factors unrelated to the classification rule on the training data. The error estimator is a random variable through as and the error estimate is the value of n given realization of Sn, and that's the real number, unless otherwise stated it is meant to be approximation to the conditional probability of error. Error estimator can be non-randomized and randomized. Non-randomized is like when the is not fixed. The yes, it's non-randomized given the training data. The estimator is fixed. There are no internal random factors. Randomized given the training data, the estimator is not fixed quantity. It's still random variable through. Holdout estimator, which we have talked before, right? Here we assume that there is a set of testing data, which is not using classifier design, and we define it like in this way. Since SM is a random and independent from the training data, this is a randomized error estimator. So holdout is a randomized error estimator. So how it works? It works that way. So first we have a training set and a test set. So we have our data and we have split it into two. And what we do, we add algorithm to the training set, and we start uh, developing a classifier. And then we just like what we do, we just only just put like the test set. We use a test set just to check and examine the performance of connect of the developed classifier. It's like very simple. Despite its many nice properties, holdout estimator has a big drawback. In practice, one has to split the available dataset into sample of training and samples for testing. Hence, which is usually larger than the so that estimator is pessimistically biased. If the bias is small, there is no problem, but in small sample cases, the bias can be large, or 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 perhaps more concern is the variance if the number of test samples is small, then the variance of the usually large. So the problem is that for the small sample sizes, holdout estimator is not very good. As you can see, for small sample data, one must train and test on full. For small sample data, one must train and test on the full data set. You see, if the error estimation number of samples so small region, we have this one. Data efficiency holdout. And now let's ask DeepSeek to give us the sample. So holdout estimator splits the data. Okay, so we've got an example. It's very cool. We love that. We go into the next one. Okay, so yeah, in the conclusion, with the whole lot estimator, we've got the main two problems. Is that when we're trying to evaluate the model on the small sample data set, it's just like the holdout may really experience problems because it like the uh, its metrics may not be so reliable. Error estimation metrics, and the second problem due its um, uh, dependence on how the data is split, so it's like high variance. Okay. However, we also have another alternatives to holdout. So the first is the substitution, cross-validation, and bootstrap methods, right? So let's go to the resubstitution. Resubstitution is the simplest alternative. It's simply the apparent error or the error of the training data. So it's like very simple. Its advantages are that it's non-randomized, estimated, and low computation complexity. It's lightning fast, so attractive in applications with a large dataset. Its biggest drawback is that usually optimistically biased. The bias tends to be larger for complex classification rules due to overfitting. As an extreme example, we have the 1 rule for each, regardless of the data. Okay, so yeah, let's just write. Let's go here. The outcome of applying it to a training set is classifier. The proportion of the samples in some is classified as a substitution estimate. Substitution estimator will generally lead to an overly optimistic estimate of the performance. This is not surprising because learning algorithm attempts to fit some to some extent. Therefore, its naturally performs better on rather than independent. So it's optimistically biased. Is that all? Okay, so okay, we go here. It's non-randomized. It's fixed. We have a bivariate Gaussian model with known parameters to generate the training data and train NLD classifier. Okay, like in the same way, explain me resubstitution method. Let's go. So substitution is non-randomized. It's fixed. However, yeah, it's fixed because why the reason why holdout is randomized, because like like in general you when you start like splitting your data set, you just like can randomly like shuffle the data and randomly select 20 or 25% of your test set, but the rest will be used as a training data, right? Or you also can like take some chunks and like and create a validation data. By the way, this is important thing. If you really do not understand what is a validation data set, it's very important to know. I remember myself when I was really like when I was not uh, so experienced in machine learning, etc., and I was really thinking about what is actually uh, like the validation data set and why we need to use that and etc. And the thing is that when you training a classifier, right, you have a training data and a test data. When you have a training data, during the training classifier, you see like the error after each epoch, the loss, I mean, and for like and how the accuracy is increasing epoch after epoch, right? It's very cool. However, uh, and only then you test. Only then after you finish training, you just only then you need to put that on a test. And that point, you don't really know how well it will work, on the test data. You see, so you're just like wondering, okay, maybe it might work well like on a training, but unfortunately during the training I'm not able to test it like on the test data. So I will finish on the training, like on the training data. On the then I will just start testing like on the test data. It might take time, right? But what if I will tell you that you could like during the training uh, phase, you could already test how your model works on the unseen data, and that is why you need a validation set. So, for example, you're training on the training data, right? And but at the same time, after the each epoch, what you do first, you see the loss and performance accuracy on the training data. At the same time, what you do, you're just like uh, just checking the performance of your model on the unseen data, right? On the validation data, and then you will be able like to see how well your model works, like, and you will see the general picture, right? Or because, for example, it might be the case when your model works really well on the training data but works very bad on the validation data. It means that you're experiencing overfitting. So in this case, whether you have to reduce the number of parameters or add any other regularization techniques to that, your model will have a higher percentage of generalization, which is very important, which is very crucial. So that's the thing. Okay, so we're still trying to connect to the DeepSeek. Let's see. So, by the way, do DeepSeek have pricing? So we go to a API platform. Okay, let's ask at the same time ChatGPT how it works. All right, so DeepSeek doesn't want to work now. It's very strange. However, it's not that strange. It means that like DeepSeek is always like experiences kind of problems. Yeah. However, yeah, I would love to buy like a pro version of DeepSeek so that I could use it more. Okay, we're asking. No, not hold out. Sorry. Just resubstitutions, excuse me. So what ChatGPT gives us? Substitution evaluation is a basic method for assessing the performance of a machine learning model. In this technique, the model is trained and tested on the same data set, meaning that there is no separate validation or test set. The model's accuracy is measured based on how well it predicts the training data it has already seen. Train model A model is trained on the dataset, and the model is valid on the same dataset it was trained on. Calculate the performance metrics, calculate accuracy, precision, calculate them. Simple and easy to implement, gives a quick initial estimate of the performance. This is what about advantages. However, what about the disadvantages? Leads to overfitting because the model memorizes training data, does not generalize well on unseen data, provides an overly optimistic estimate of the model's true performance. Let's say we are training a simple classification model on a small data set like this one, right? So we have 1.1.2, 2.5, 3.1, 0.9, and we've got all these features of this other labels. And we're training the classification model that tests the model on the same data set. So we've got accuracy 100. This is how accuracy is misleading because the model may fail on new, unseen data. Why is this pretty problematic? Since we tested on the model on the same data, it learned from the accuracy is biased and doesn't reflect how real-world performance. To get more reliable estimate, we should use the cross-validation of separate trans split test. You see, that's the reason. That's the fact that we really have to know that. Okay. Okay. So we know this one, and we know how it works, right? So it's very cool. So the substitution of here apparent error is less than true error. This neither means that the estimator is optimistic, nor the optimism implies optimistic bias. Remember that to be an optimistic estimator, we mean the expectation behavior on average is less than expected true error. It's substitution in practice. Now we are moving to cross-validation. Yeah. I hope you guys all know what is a cross-validation. However, yeah, we will talk about it again. And we start with this. Cross-validation removes an optimism from substitution by employing the test points not used in the classifier design. In k-fold cross-validation, the trained data set is partitioned to k folds, like for example 5, 6, or 7. None doesn't matter. Each fold contains samples n samples that are left or out of trained data and used as a test set. The process is repeated k times, once for each fold, and the estimate of the overall proportion errors committed on all folds, where x is a simple set in the ith fold. The process can be repeated by using different partitions and by averaging their results, and averaging helps to reduce the internal variance. This is a randomized error estimator. Why? And it can be slow estimator for large. It's randomized because like we randomly like create this kind of faults and we not really regulate. We're not fixing it. Yeah, it can be a slow estimator for large N and K. Cross-validation is advertised as unbiased, but it's unbiased as an estimator of provided the faults are picked randomly. Usually, this means that it's pessimistically biased as estimator of a. The most important drawback on cross-validation, however, is its large variability on small sample sets. I'll leave it now. Yeah, so cross-validation, right? So, and I'll ask you, do the same for cross-validation. Yeah, boy. We are in accord. Puck. Do you know who is the puck? I hope you know who is the puck, to be honest. Have you ever played Dota? Or you have not, you just really have to know to check who is this guy. Okay. All right. So performance of the computer. Cross-validation is a more reliable method for evaluating a machine learning model compared to substitution. Instead of training and testing on the same dataset, cross-validation splits the data into multiple parts to ensure better generalization. Divide the dataset into key equal size subsets folds, train on key folds, and test on the remaining fold. Yeah. So how it works? For example, guys, now I'm going to show you something. For example, you've got where I can use, is here anything like, can I draw here? Okay, maybe I draw things. No, not this one, not this one. Maybe this one. So I'm creating a document here. So let's start with, just let me find here. Gosh, I have here no thing to. Okay, let me find. Delete. Think more. Okay. So we have our data set, which is this one, right? And in the cross-validation, we can state that we have 3k fold. So we have 1, 2, and 3, right? So we can say that the first 2 folds will be used as a train. You see, will be used as a train, and that this one will be used as a test. So this is actually our first thing what we can do, right? So after we do this, for this is will be our first iteration, and we get here specific error. We get here specific error will be error 1. Then what we can do is that we can again randomly shuffle. So or we just can say that again we take our train and we say that this this and the last 2 folds will be used as a train, and this one will be used as a test. You see? And then again, this will be iteration 2, and we have error estimation like 2. The same thing we do for the third. So we can say like, this were our train, and the third, actually the middle will be used as a test. So we have here like 3 of them. So what we do that we just like sum them, and what we do, so I have to sum all the I have to sum and divide by the number of this, but the number of folds. So then I will find the average. This is important to know, okay? A, V, and G. You see how it works, okay? So let's get back. So train the k folds and repeat this k times, each time using different call fold testing. Compute performance metrics, accuracy, precision, recall for each fold. Average the results to get more general estimate of the models. So what is its advantages? So So again, we have here example to fault assignments. Step for 5-fold cross validation. Okay. So how many features are how many observations we have here? We have here 5 observations, and we're going to have 5 faults. You see? So the first fault 1 test. So the fault 1 test is a row 1. The fourth are used as a train. The same thing I do for, like for the second in the fault 2, I say the row 2 will be a test, and the one from 3 to 5 will be the train. In the fault 3, I say that row 3 will be my test, and from 1 to 2 and from 4 to 5 will be my train, right? From fault 4, I say that for the fault 4, I say that row 4 will be my train, test, and from the first to third and the fifth rows will be are my train. And and finally for the fault 5, I say that row 5 will be actually my test, and from first to 4 will be train the model on 4 faults, test on the one remaining fault. This is how it works. Repeat this 5 times, each fault gets the tested once. Compute the accuracy for each fault and average the results. You see? So I've got here like 5 different accuracies for 5 different faults, and what I do is that I just like to average them and then get the average. So yeah. So if we compare like the buff or substitution to a cross validation in terms of bias, our substitution actually is optimistically biased, which means that it really overestimates the accuracy. However, the cross validation is just like really uh, um, uh, has a better generalization and like pessimistically biased. Computation cost through substitution is low. However, like cross validation, it will be higher if it will be used like for like on the large data sets. So suitability is simple, actually suitable, fast, but unreliable. Um, substitution is not unreliable, but more reliable. But cross validation is more reliable, preferred for small data sets. So this is what we know about this one. Okay, we go forward. All right, so 1 hour of work, but I'm not tired yet. Okay, so so this is actually, let's talk about leaving out error estimator. So how it works? So we have a sample. Okay, yeah, if I remember correctly about how actually how works the how works the by the way, this is actually a threshold filter, salt and pepper filter, no matter how you may call it. So how it works? Um, what it does is that I hope we're not going to have. Okay, can I pause it a bit? Is lowest manner for large. It's randomized because like we randomly like create this kind of faults and we not really regulate. Uh, we're not fixing it. Yeah, it can be as slow as matter for large N and K. Cross validation is advertised as on its appliance as
Промокнуть рабочий какой-то. Подожди, сейчас не заказывай, я сейчас узнаю у друга, он с кем шарит. Я понимаю, да. Я Ну ладно. А чё так глубоко? Кристина, то отдельно, где он сказал, что мама сказала, что ты бываешь. На его тоже сказал. Вот. Ты не сказала, что поздравить. Ты привет. Сделал поздравить. Не сказала, что поздравить. Ты сказала, машина, да. Как ты тебя? Ну, чё было, да? Ты поздравил, да? Все, зачем мне вот, смотри, у тебя есть шанс еще нравится. Что ты спал? Вот я это ну, правда, правда. Вообще у них угарно, правда, да. Да. Угар пойдет. Пишет, пишет специально, ну, коллеги. Я там не может ситуация была у коллеги. Почти. Тебя с Валерием пообщаться. Вообще ничего, вообще ничего. Ну да, примерно так. Вообще, вот это для этому пришел. Короче, ты представляешь, оживиться когда, да? Сколько это стоит, нам до 16? Да, нет, совсем короче. Да, ну сколько, 17 возьмем, да, 17 или 15. Какое? Ничего там такого. Это можно 21 отбьем, а че кажи? Если я сам скажу, файл на 17, да. Я не сказал, не 20 нормально. Потому что там 25 это где-то 25. Она не 25? А почему без 25? Да, 25 нормально. 20. Давайте заказывай. Только у него фон нормальный, там они красивые. Угу. А какой нам адрес там был до этого? Я лучше Андрея Лики подумаю. Да. Доставку до дома. Да. Ну все, давай тогда закидывай, потом карту. Только скажи, смотри, чтобы тюльпаны были не просто типа одного цвета, чтобы желтый, зеленый, белый был такой. Разного цвета, да. Ага. И пусть их фото отправят, давай.
So, guys, I'm back. Let's continue our work on what we've been working on. All right. So, so that is the thing. I do the same with what how it's called? Is substitutions matter? No. We will go to here. Leave it one out. To be honest, I know what is the leaving out technique, so let's remember it. Uh, so this is the technique when you, for example, you have like 5 different observations. What you do is just like uh, you have 5 observations. You just like erase one observation and do it like on the fourth or something like this one. To be honest, I don't remember. Leaving out validation is a special case of k-fold cross-validation where k equals to n. This means that for each iteration, the model is trained on n1 samples and tested on the remaining sample. This process is repeated n times, ensuring that each data point is used to test exactly at once. For each data point in the dataset, remove that single data point from the dataset. Yeah, that's what I thought. I talked about train the model on the remaining data points, test the model on the single left out data point, record accuracy on the metric, repeat all of the data points. So this is actually yeah, uses all available data. So it's like unbiased, uses all. Yeah, so for example, we have again our five samples. What we do, so we say that the train is like this is our train and this is our test, right? So we compute accuracy for this iteration, and then what we do is the following. That again we say that this will be our my test. The left will and the left out will be my train. So this is we do it for 5 times. You might ask me what's the difference between the lift and out. Yeah. So um, this is how it works. So yeah, let's see. We have a sample. So I have a sample, and I'm splitting it to training set, where I have removed one, and test set. So I start doing developing a classifier. Okay. So, алло. Да-да. Дома. Мгм. Десятерых, десятерых. Что с ними делаем? Да. Ничего. Да, она вот улетела. Ну, уехала и улетела вот это, в Испанию. Да. Вы что делаете? Да? Погода хорошая, да, кажется? Бавсаки. Мучное слишком вредно. Бавсаки, что потом? Что еще возьмем? Может быть... Ну, мучное не надо, да, мучное не надо. Может быть, какой-нибудь там... Ну ладно, что, ничего не будем брать, да? Может, какие-то там салаты есть? Я бы от салата бы не отказался бы, да. Типа, какой-то такой ну вот острый морковный хотелось бы. Прям, ох, как хорошо. М. Нет, я говорю, тогда вы можете хотя бы тогда сделать салат? Я не знаю, просто сделать своими руками. А помнишь, что я делал салат, когда мы жили еще на Кошхарбаева? Он такой какой-то был, не помню, что салат был такой вкусный. А? М, Нет, на Кошхарбаеве, когда мы комнату снимали. Когда комнату ты снимала, матушка, да. Да-да, вы снимали комнату. Вы снимали комнату. Да-да-да-да-да, морковь с чесноком. Морковь с чесноком. Да-да-да-да-да-да-да-да-да. А потом пойду, не сейчас. Мгм. Всё, целую, пока.
Алло,
Привет.
привет.
Это я Жан.
О, как дела?
Нормально, я
Что
снова выхватила у вас на телефон, пока он там. Короче, Даняр, я приглашаю тебя на свидание.
О, вау, давай сходим. Может, по Данеру, по Эльвире, слышал? Хорошее место.
А что ты смеешься? Почему бы нет?
Давай.
Как насчет завтра?
Давай, можно.
Да,
Давай, да сядь куда-нибудь, я закажу. Смотрим.
засядем.
Какой-нибудь
Фильм, давай.
Все, класс, договорились.
Все, давай, сейчас я передам трубку Асанали. Алло, салам.
Алло, да, салам, как дела?
Чё, бро, как ты?
Да, ничего, неплохо.
Чё там, чё делаешь?
Вот в комнате убираюсь чутка. Сейчас хочу в универ пойти. Прицелку.
Чарить будешь?
Да, там надо делать много. Вот. Че, мега еще надо сходить.
Чё будешь делать?
Там марка делать, потом еще надо по ресерчу кое-что сделать. Примерно так.
Чё, завтра пойдем кушать донера?
Завтра? Я думал, сегодня. Ну, давай завтра, окей.
А потому что сегодня почему не получилось скажи мне, я сегодня дома остался.
Ну, все, окей. Все,
Предлагаю завтра.
давай.
Да?
Тогда.
Хотел тебя предупредить. Что там этот Жанат Капас что-то там написал, блядь, не в тему 7 утра там, бля.
Короче, ты уже понял, да? Странно так. 7 утра еще написал.
Да.
Это наши следующие лапки. Ой, я тебе забыл лапку скинуть. Да, по идее, еще я сам даже не заметил. Я тебе сегодня скину.
Давай, Даняр, скинь, а то, не дай бог, скажешь, типа, что вы так поздно сдаете?
Да. Это, да, по-моему, знаешь, это какие лапки он говорит? Это аж 8-я лапа или 7-я? По-моему.
Угу.
Потом аж.
Не, ну это же, это же экстра же.
Да, я не знаю, может, надо.
Не-не-не. Он мне сам говорил, он понял, я точно говорил.
Окей. Просто какой проект будет? Может, что-то будет там в проекте?
Проект мы сами должны выбрать, типа Computer Vision, не знаю. Там.
Блин, странно, ничего не говорят. Не понимаешь, что делать.
Потому что, блядь, никто и не спрашивает, ёпта.
Да. Ну, знаешь, я спросил, все игнорят, так ладно, может, так надо, не стал спрашивать.
Что ты не стал спрашивать?
Пойди, да, надо спросить там кое-что.
Да. Что-то Амина не чалишь пока?
Пока нет. Надо потом.
Да, ну ты зачалишь, если что.
Что-то надо открыть, сделать. Я и проект прополз написать.
Ебать. Точняк. Проползал, ёпта. Ох, ёпта. Тяжело.
Ну да. И не надо написать тогда этой. Айран надо написать. Точно.
Да, ну ты больше не пиши эту группу, блядь, никто не хочет писать.
Я уже понял, что кто-то либо болеет,
либо притворяется. Да пошли нахер, скажи.
Ну, в целом, мне, знаешь, не впервые. Так что нормально. Да. Ну, типа, часто встречаю людей, наверное.
Как я, например, да, тоже.
Где-то нет, ну, по идее нет. Не помню, что ты игнорил.
Чтобы я игнорил?
Ну, ты в этой группе пишешь, кстати, красавчик.
Да.
Каждый раз пишешь.
Поддерживаю своего, бро.
Да, кстати, да. За поддержку.
Может, как там, чё вы все, блядь, где-то бесите уже?
Бесите уже. Не пиши, нормально.
Да что. Да, это воспримут этот, жестко воспримут.
Жестко воспримут. Да. Не, знаешь, что, просто, знаешь, они сами просили, типа, погуляем, мы хотим погулять. Такая, ну, окей. И не делал. Теперь они что-то молчат. Я не понимаю людей. Я запутался. Ладно.
Сучки, да?
Угу. Да.
В точку Даняр говорит, ненормально.
Да. Я прислал понимать людей. Чё у тебя как? Новостей нет?
Новостей нет. Пока все так же.
Не писали, да?
Бузои, да нет, может, кажется, ГГ.
Ну, не знаю. Pray for the best, да? Pray for the best. Pray for the best.
Да. Ну там он точно ГГВП, кажется.
Ну смотри, сколько осталось? 2 месяца, да?
Нет, осталось 27 дней.
В смысле, до 31 марта?
Да.
Я думал, апреля. Апреля же, нет?
Нет, до марта.
Ё-моё. Ну да. Я думал, вообще есть 2 месяца. Я думал, ну...
Не.
Ну ты пейпер, кстати, сабмитнул?
Ну, проф проверяет, наверное, еще.
Что-то долго он проверяет. Он же проверил, по идее. Что там проверять?
Как раз
Нет?
завтра в универ пойду, спрошу, что там, А он же болел, может, болеет. Ну, не знаю, посмотрим, спрошу.
Точно уже болеет. Все, ладно. Да, понятно. Тогда не беспокой.
Тебе вообще профа не жалко, да, вообще, да?
Согласен. Я не забыл, что он болеет просто.
Не, ну зато все равно просто email напишу, типа, did you take a look? Все равно напишу, напомню.
Скажи, типа, с выздоровлением или типа, ага.
Я скажу, а Даняр спрашивает, чего вы не проверяете?
Чего не
Он
проверяете?
скажет, заебал меня.
Постоянно
Да.
болею, да.
На уроке, блядь, что-то спрашивает, блядь, здесь что-то спрашивает, заебал.
Блин, реки. Он меня прям аж запомнил, кстати.
А?
Он меня прям запомнил.
Да. Такой заебался, он что-то спрашивает.
Да.
Такие вот дела. Завтра я в универ приду,
Ну все, давай.
пообщаемся.
Давай. Конечно.
То что, кстати, а что тебе там? А я же говорила, она то что, просто тут трубку мне взяла?
Она это, в общем, пригласила меня на свидание.
Ебало. Когда? На завтра, что ли?
Да, после как мы поедим до Неры, я должна случиться.
Да нормально. Окей.
Все. Угу.
Я думал, просто прямо сейчас, или там что-то. Ну, все, это нормально. Да, норм.
Все, пас.
Давай тогда, Бродский, на связи.
Давай, на связи.
Ага, да.
И вот имиджевый фон, мне кажется, имиджевый фон у Родины Медиа последний год был очень хороший. Вспомнил отношение к Родине Медиа там даже, в последний сезон, правда, была команда, в которой играла очень много ярких медийных ребят, и при этом играли они там неплохо, и, в принципе, добрый вайб очень был у команды.
Парадокс, что когда Текила перестал быть злодеем в медиалиге, он, типа, и перестал в ней находиться. То, что реально, вот это сезон вообще как добряк такой.
Ну и при этом, кстати, к нему очень изменилось
Так я про это говорю,
отношение.
реально оно изменилось.
К нему очень высокая стала степень лояльности. Мне кажется, очень изменился отношение.
Просто тем более, что он в целом адекватный мужик, который ради шоу вкидывает, а за пределы, знаешь, вот этих камер он не уносит с собой никакие вот эти...
Ну, бывает, лишника тоже дает.
Ну, бывает, но ты тоже, брат. И Володя тоже. Вы как таких, вы, в принципе, в одной команде не просто так собрались.
Ну,
3 тусовщика.
Это вообще, что он здесь позволил? Слушайте.
The bootstrap sample corresponds to a random sample of size from empirical distribution. It consists of equality. By the way, I know the exact value of a bootstrap, 0.63. The bootstrap sample sum of the original training samples will appear multiple items, whereas other will not appear at all. The basic bootstrap zero error estimator consists of testing on the samples left out of the bootstrap sample and averaging over several bootstrap samples. This is similar to cross-validation, but here the classification rule operates on n sample points. Do the same for bootstrap. Okay.